Hello guys, in this video we are going to continue on the traveling salesperson problem. These are the topics of this chapter, and in this video we are going to look at bullet number 2, which is about the exact methods to solve the traveling salesperson problem. Specifically, we are going to look at two classical mathematical models that can be used to solve the traveling salesperson problem. So let us begin with our first formulation. In this formulation, our main parameter is the distance from city I to city J, represented by Dij. As a convention, we assume that the distance from city I to city I is a very high value. Our main variable is Xij. It is a binary variable and it is equal to 1 if city J is reached from city I. Otherwise, it is 0. So now let us formulate the problem. Our goal is to minimize the total tour distance. Let us take an example and see how to measure the tour distance. Let us say we have 5 cities represented by these nodes 1, 2, 3, 4, 5, and let us say the distance between city 1 and city 2 is represented by this blue line. So all the cities have some distance, some value. And now I am going to make this tour. On the graph, this is how it looks. Now the tour distance is nothing but the sum of those distances which I have traveled in this tour, which is nothing but D12 and D23, D34, D45 and D5. Now to select these distances from all the distances, I am going to multiply the distances with the decision variable. So now you can see the tour distance is nothing but the sum of all these distances. And all the other distances which I didn't travel will be automatically 0. For example, if I have a term like this, D13X13, it will be 0 because I didn't travel that path. To summarize, the total tour distance can be written as the sum of lengths of those arcs that are selected in tour, which is nothing but summation over I, summation over j, dij, xij. Now let us look at the constraints. The first constraint is there should be exactly one city from which you are entering the city. Let us take city number j. Now you can enter city J from any of these n cities except city J, of course. The constraint says that from all these possible cities, we can pick only one city and enter city J. That is from X1J, X2J, so on, Xnj, I need to pick exactly one of the cities, and this should be repeated for all possible cities. Okay, so this is the constraint. The next constraint is exactly one exit city for a given city. Let us take an example. Let us say we are in city I. From city I, you can go to any of these cities. Now, according to this constraint, you can go only to one of these cities. That is from Xi1 or Xi2 or Xin. I should pick exactly one of the exit city. and this should be done for all I. Therefore, the constraint is written like this. And last but not the least, you have the binary restrictions on the variable x, and this is how it's written, and this is our TSP formulation. I am going to call this formulation as PTSP0. You can see that there are certain structures in this formulation. For example, these constraints are called as the assignment problem constraints. One of the speciality of these constraints is if you solve the relaxed version of this problem, you will be getting an integer solution. Now let us take an example and see if this formulation is correct. In this example, we have 5 cities, and here is the corresponding distance data between every pair. For example, distance from city 1 to city 2 is 15 kilometers. From city 1 to city 3 is 20 kilometers, so on and so forth. Similarly, from city 2 to city 3, it is 5 kilometers, and so on and so forth. And let us solve this formulation using any commercial solver like Cplex or Groovy. Even linear programming solvers can solve it. And when I solve this problem, this is the optimal solution that I got. Let us draw the optimal solution. And looking at this solution, we can see that the tour was going from city 1 to 5 to 4 to 2 to 3 to 1. Now let us try with another data. Now when I solve this problem, this is a solution that I got. Let us plot this solution. This is how the solution looks like. Oh, there is a problem here. It looks like you're going from 1 to 3 and then 3 to 1. On the other side, you are going from 2 to 5, 5 to 4 and 4 to 2. So this is not a TSP feasible solution. Although we have the optimal solution for this formulation, it is an infeasible solution to the TSP problem. That means this formulation has some deficiency. It doesn't capture the entire TSP constraints. And we are going to see in the next slide how to fix those issues. In order to fix the issues, we need to add some constraints to this problem such that these subtours are removed. Now what is a subtour? A subtour is a tour that is not connecting all the cities. Constraints that are added to this problem to break these subtours are called as subtour breaking constraints. Can you identify any of those subtour breaking constraints? You can say that not both the arcs from this subtour, which is 1, 3 or 3, 1, should be included in the tour, or not all the arcs in this subtour should be included in the tour. So you have to break only one of the subtours. These constraints can be written like this. So from these 2 arcs, select 1, and from these 3, select any 2. In general, we can write this constraint as follows. From all the arcs of subtour, at least one of the arcs should be removed. This symbol here is the cardinality of the subtour. It means the number of arcs you have in the subtour. So this constraint basically says from all the arcs of the subtour, you have to remove one of the arcs at least. Now how to use this constraint? You solve the PTSP0, and then if you find any subtours, you add such constraint for one of the subtours and resolve this PTSP0. And you repeat the process until you find that there are no subtours in your solution. And this approach of adding the constraint after you solve the problem can be extended to build a cutting plane method. However, we are not going to build a cutting plane method here. We are going to build a branch and bound based method. So instead of using this constraint as is, we are going to convert this constraint into the logical form, which is either x13 is 0 or x31 is 0. Similarly, this constraint can be broken down as x25 is 0 or x54 is 0 or x42 is 0. So one of them should be 0. To summarize, to break one of these subtours, you have to either go with this set of conditions or with this set of conditions. And here is the big picture of solving the TSP problem using Formulation-1. You first solve PTSP0 assignment problem. If you find no subtours, then that's it. You found the optimal solution for TSP. If you found any subtour, then pick one of the subtour and solve many subproblems. In each subproblem, you have the same formulation as that of the initial formulation, or you can say the parent formulation, plus one additional constraint, and that additional constraint is based on the arcs of the subtour. Let us take an example and see how this method works. In this example, we have 5 cities, and this is the distance data. First, we are going to learn how to solve the assignment problem using the Hungarian method, and then we will see how to implement this branch and bound algorithm. So how does the Hungarian method works? Well, first we create the reduced cost matrix from the distance matrix. In order to create the reduced cost matrix, from each row you subtract the minimum distance from all the elements. So 3 is the minimum in the first row, 2 is the minimum in the second row, so on and so forth. So I'll be subtracting 3 from all the elements in this row. Similarly, I'll be subtracting 2 from all the elements in this row. Now, from each column, I'll be subtracting the minimum element. So here are the minimum elements, and we'll be subtracting it from all the columns. And this matrix is called as the reduced cost matrix. This is the end of step 1. In step 2, we are going to cover all the zeros with the minimum number of horizontal and vertical lines. If the minimum number of horizontal and vertical lines are equal to the number of cities, then we have the solution for the assignment problem. If not, then you look at the smallest uncovered number. For example, here it is 1, and you subtract that smallest uncovered number from all the uncovered numbers, and you add it to the numbers which are twice covered. So here I subtracted 1 from all the uncovered numbers and added it to the twice covered numbers. Now in the new matrix, I try to cover the zeros with minimum number of horizontal and vertical lines. If the minimum number of lines is equal to the number of cities, then I have a solution. And here we need 5 minimum lines to cover all the zeros. So that means I have the solution for the assignment problem. Now how to identify the solution? Well, you try to find those columns which contain only one zero. For example, here you have column corresponding to city 3 and city 5 with only one zero. So that means you are going to go from city 1 to city 3 and from city 2 to city 5. So you are going to eliminate those rows and those columns. From the remaining rows and columns, you try to identify the column with only one zero. And here it is for city number 4. It means you go from city number 5 to city number 4. Now you delete the corresponding column and row. Now from the undeleted columns, try to identify the columns with single zero. And here you have these two columns. That means from city 3 you can go to city 1, and from city 4 you can go to city number 2. So that is how the solution is obtained from the Hungarian method. So here you have x13, x25, x54 equals to 1, and x31 and x42 equals to 1, and rest all are zeros. Graphically it shows us that there are subtours. Now let us see how we can break the subtours using our proposed mechanism, which is this. Using this mechanism, let us see how we can break the subtours. Our method is based on branch and bound enumeration tree. So at the beginning, we solved the root relaxation, which is PTSP0, and we found 2 subtours. Now the relaxed problem will give us the best bound, and since the objective function type is to minimize, we are going to get the lower bound. So the lower bound here will be 15. Now how to get an upper bound for this problem? Upper bound for this problem is nothing but a feasible solution. And for TSP you can get very easily a feasible solution. For example, I could just say going from 1, 2, 3, 4, 5 and coming back to 1 is a feasible solution for TSP. And the corresponding objective function value is 29. So that will be the upper bound for this problem. Now, from these two subtours, we are going to break one of the subtours. Now, which subtour to select is a part of the strategy. Sometimes we go with the subtour that contains minimum number of arcs. Sometimes we go with the subtour that contains maximum number of arcs. Depending on the strategy, you can select the subtour to break. Once you select the subtour, then you are going to identify the branching variables. For example, here if I select the subtour 131, then the branching variables will be x13 and x31. If I am going to go with the other subtour, then I will have three branching variables, x25, x54 and x42. One of the big differences from this TSP branch and bound to the general branch and bound is a parent node can have more than two childs. For example, if I break this subtour, then I will have 3 childs. And the other difference from the conventional branch and bound is all the branching directions will be branched down. So now I am going to select this subtour because it has few number of arcs, and based on the number of arcs I will have the childs. Here I have one child for x13 equals to 0 and I have another child for x31 equals to 0. Now from these two childs I am going to select one of the childs and solve. Selecting the childs is also part of the strategy. You can look at the corresponding cost in the cost matrix and see which child to select first. Here D13 is 3 and D31 is 4. In this example, I am going to select the child which has the highest cost. So here D31 has the highest cost and that will be the next child to be processed. The nodes will be numbered according to their processing. At this node, I am going to solve the problem which has the same objective function type. All the constraints are same from PTSP 0 plus one additional constraint which is x31 equals to 0. But I am not going to add this constraint. Instead, I am going to solve the same PTSP 0 with the change in the data matrix, and that change will be D31 is infinity. So I am not going to change the constraints of the LP problem. Instead, I am going to change the data, and changing the data will make sure that this restriction is satisfied. The reason why I am not adding this constraint and I am changing the data is I am trying to preserve the assignment structure in the problem. Preserving the assignment structure will ensure that solving the LP relaxation of the problem will still give the integer feasible solution. So let us solve the PTSP1 problem with this distance. So the distance is being changed here and we solved the problem, and then we found that the optimal solution is a complete tour with the objective function value of 16 units. Now since this is an integer feasible solution, I have a better upper bound. Also this node is dead because of the integer feasible solution. Now I have one open node, and at this node I am going to solve the same formulation as PTSP 0, except that the distance matrix here will be modified like this. You will have one element which will be changed to infinite. Here is the distance matrix that we used at this node, and when I solve this problem using Hungarian method, this is the solution. Now I have two subtours and the objective function value is 17. Now you can see that the best integer solution that I can get from here is 17 units. But I already have integer solution with value 16. This implies this node here is dominated by this node. So I can kill this node by the label dis. So all the leaf nodes are dead and we have the solution for the TSP problem. And the optimal solution is 134251. Let us take another example. In this example we have 8 cities and this is the distance between every pair. Let us start with the upper and lower bounds. The upper bound for TSP problem is nothing but any feasible solution. For example, I'm going to take a feasible solution 187,645,231, and the corresponding objective function value for this solution will be the upper bound. To get the lower bound, we solve the LP relaxation using Hungarian method, and when I did that, that is the objective function value which will be assigned to the lower bound, and I have two subtours to break. From these two subtours, I am going to pick one of them arbitrarily because they have the same cardinality. Now to break this subtour, I need 4 child for 4 arcs. So I have one child for x18 equals to 0. I have one child for x68 equals to 0. I have another child for x64 equals to 0. And another child node for x41 equals to 0. All these childs will be solved with the same constraints as that of PTSP0. The only difference will be the data. Here I will have D18 equals to infinity. Here I will have D86 equals to infinity. Here I will have D64 equals to infinity. And here I will have D41 equals to infinity. So those are the minor changes that I will have at every node. Now from these open nodes, I am going to select the node which has the highest distance value. Here the distance value is 7 units. Here the distance value is 5 units. Here the distance value is 5 units, and here the distance value is 3 units. So among these 4, the one with the highest is x18, which is of the value 7. So I'm going to solve this node first. When I solve this node, that's the objective function that we got and the corresponding solution. It is an integer feasible solution, and the objective function value improved the upper bound. Now from these remaining nodes, I am going to select the node which has the highest value. That will be x41. When I solve this problem, I got z equals to 46 and I got 3 subtours. If I further process this node, the best objective function that I am going to get is 46, and I already have 43. That means this node is killed by the label DIS. The next child that I am going to solve will be this one, and the objective function value here is 48, and it also contains subtours. So this node is also dominated by the IFS solution. When I solve this last node remaining, I get the objective function value is 46, and these are the subtours. And based on this IFS solution, I can kill this node by the label DIS. So all the leaf nodes are dead, and we can conclude that this solution z equals to 43 is the optimal solution. So that is all what we have in the formulation 1. In the next video, we are going to look at formulation 2.